Chapter 7, Estimation with Confidence Intervals. This is section 7.2, Confidence Interval for a Population Mean using the normal Z statistic. All right, so here's our old terminology. All right, old terminology that we'll be needing. We'll look at some old terminology, then some new terminology. A parameter is a single number that describes a population. All right, such as the average score in our course on exam 2. All right. A statistic is a single number that describes a sample. So that would be like the average score on exam 2 for um, for let's say 8 students. Okay. We know that the statistic is lying to us about by the parameter, which really justifies all of what we're going to be doing in chapter 7. All right, we're going to use the statistic and we're going to analyze the sampling distribution and use the standard error to build a confidence interval to capture the parameter. Okay, so the sampling distribution, that's referring to our new normal curve. Okay, our new normal curve that describes the variation, it describes the overall behavior of the statistic. Okay, so that's what we mean by the sampling distribution. So we often draw pictures, as we saw in chapter 6, that look like this. Okay, where we're talking about the behavior of X bar. That's that little X bar in the corner is talking about. It's saying like, okay, that's how the behavior of X bar would behave. Right in the middle, we saw because X bar is the unbiased minimum variance estimator of mu, right in the middle is going to be mu. Okay, so that's the sampling distribution. The standard error is describing how much spread is in this new normal curve. So that's sigma subscript X bar, which equals the original population divided by the square root of the sample size. That's describing how much spread there is in our new normal curve. All right, in terms of our new terminology, one is the point estimate. That's a single value guess at the value of the parameter. Okay, the interval estimate is a multi-value guess at the value of the parameter. Okay, and then the critical value, as we're going to see, it's a number right around 2, and we'll talk more about that in a moment. Okay, but just if you squint your eyes a bit, you'll see the number 2. It's going to be right around 2. Okay. All right, so point estimate, that's our single value guess. What is a point estimate for mu? Let's say mu is the true mean exam 2 score. All right, a point estimate is a single value guess aimed at capturing what mu really is. So let's say that we sampled 8 students and we got an X bar of, I don't know, 164, right? We know that X bar is not going to equal mu, almost certainly not going to equal mu, right? X bar is just a moment in time where we have 8 students and we calculated a statistic from those 8 students, all right? So a single value guess here, that's X bar, that comes from the 8 students. So an interval estimate is a multi-value guess, okay? So if my sample mean is 164, which comes from the sample of 8, and I want to know the true mean exam 2 score, all right, all we mean with a multi-value guess is give me more than one value that represents the actual value of mu. So if I go to the number line here and I find 164, well, that's a point on a number line. That's a point estimate, or you could also call it a point estimator, okay? A multi-value guess would be saying that the true mean is between 160 and 168. All right, that's what an interval looks like. There it is. That's an interval guess. Okay? So instead of just saying the average score on the exam is 164, I would say the average score on the exam is between 160 and 168. All right, let's look at our other parameter p. We'll be seeing in chapter 7 and 8 and 9 that we'll be bouncing back and forth between 2 parameters. One is mu when we're dealing with quantitative data. The other is p when we're dealing with binomial data, a series of trials, independent trials, as we saw with the binomial distribution. Okay, so what is p? Well, let's say p is just for illustration purposes here. P is the true proportion of students who have seen the matrix. Okay, the Matrix movie. Okay, we're going to call p hat. P hat will serve the same purpose as X bar. And what p hat is going to represent is the sample proportion. In other words, if I sampled 50, let's say just argument's sake here, let's say I sampled 100 UCF students, and let's say 60 of them have seen the matrix, then I can calculate p hat as 60 divided by 100, which equals 0.6. All right, that 0.6 is a point estimate. I'll put that somewhere on the number line, like right here. And that is a point estimate for the true proportion of UCF students who've seen the matrix, okay? So that's 0.6. All right, if I want to build an interval estimate, what I do is pick out other numbers, okay? Let's say that I have 50% to 70%. There we go. Now I have an interval estimate, a multi-value guess for the true percentage of UCF students who have seen the matrix. And again, it's worth emphasizing here that this p hat equals 0.6, that's describing a sample. That's a statistic. A statistic can mislead us. It's lying to us. Every time we sample 100 UCS students, we're going to get a different number that have seen the matrix. So we're concerned with the behavior overall of this p hat and then building a confidence interval knowing the behavior. And again, the behavior of p hat is it follows a normal distribution because of the central limit theorem. Okay, so serious question here. I got a serious question. Which recipe is the most secretive in history? The answer is the Coca-Cola recipe. Also, a valid answer here is the Krabby Patty formula from SpongeBob. That is also considered to be an acceptable answer. All right. What is the least secretive in history? The answer is the 95% confidence interval formula. And here it is. We take our point estimate plus or minus a letter in the alphabet, and we multiply by the standard error. Okay? Give you a moment right now to think about what letter in the alphabet do you think that would be. And it rhymes with B. It's Z, as we'll be seeing in a moment. Okay? That will generate an interval, a multi-value guess. That confidence interval formula will build an interval for us by taking the point estimate, adding and subtracting the product of these two values being multiplied together. Okay? We call this everything to the right of the plus or minus, everything to the right of the plus or minus, we call that the margin of error. Okay? So we multiply the letter in the alphabet times the standard error, we get what's called the margin of error. Okay? All together, we put this together, we get what's called the interval estimate. All right, the interval estimate. So instead of just making the numbers up that produce the interval estimate, as we did in our two examples a moment ago, all right, we're going to actually follow the methodology of statistical thinking and probability and sampling distributions and central limit theorem and everything that's led up to this in this course. That basically leads us to this formula right here. Okay, so in chapter 7.2 and 7.3, we have a parameter and a statistic, all right? Our parameter is mu, that's the true mean. The point estimate is x bar, that's the sample mean, okay? Again, we need to be aware of and thinking about the behavior of x bar so that we can know about mu. Well, x bar follows a normal distribution, and right in the middle is what the true mean really is. Right in the middle is what the true mean really is. Okay, so in chapter 7.2, we're going to have this confidence interval recipe or template, okay? We're going to have our point estimate, that's x bar, plus or minus our letter in the alphabet. Again, I said it was a letter, it's Z, okay? And if you squint your eyes enough, that Z looks a lot like a 2, okay? This notation that we use right here is a bit annoying, okay, but we have in the subscript here something we'll talk more about in chapter 8, but it's alpha over 2. That's a subscript alpha over 2, all right? We're going to multiply that whole value, whatever z alpha over 2 is. Again, that's just a letter, and it's probably going to be something near 2, all right? We're going to take that number and multiply it by the standard error, something we already know and love from chapter 6 right there, okay? That produces our interval estimate. All right, in chapter 7.3, we're going to see that the only difference is in chapter 7.3, we're going to be dealing with a small sample size. What that means is we're just going to change our distribution that produces this thing right here. That's the only real difference, okay? That's the difference. So that'll be a completely different section, as we'll see, all right? The only difference is in 7.3, we have a small sample size. Okay, and in chapter 7.4, we're going to see again that we're analyzing the behavior of our statistic, but our statistic here is p hat, and p hat follows a normal distribution because of the central limit theorem, and the center of that normal distribution is p, which is the actual value of the true proportion. Okay, so again, p hat is our statistic, which is what we call now our point estimate, and p is our parameter. All right, and that is referring to the true population proportion or true population percentage. Okay, and here we'll be looking in a future section at this formula in more detail, but it does follow the same template. It produces an interval estimate. Okay, now our letter in the alphabet is this piece right here, z alpha over 2. We'll be calling that the critical value in a moment, right? And then we multiply by the standard error, which is right here. Okay, so all told in chapter 7, we got a lot of formulas going on. Okay, the big difference between 7.2 and 7.3 is that we're just changing our letter in the alphabet. All that means is we're changing our sampling distribution, all right, to accommodate our different circumstance. In 7.2, we have what's called a large sample size, so we can use the z distribution to describe the behavior of x bar. All right. When we have a small sample size, we use the t distribution to describe the behavior of x bar. All right. Notice as well too that sigma is given up here and s is given up here. The idea is that we might not have the population standard deviation, but if our sample size is large, then s is a pretty good approximation of sigma. It's different in 7.3. If we have a small sample size, s is no longer a good approximation of sigma. All right. In order to accommodate that, we use the t distribution. All right. But the big idea here for us is when we're in 7.2 and 7.3, we have the same parameter, we have the same statistic, and we have the same margin of error that's computed in a very comparable way. We just change the distribution that we're using. Okay, and in 7.4, we actually revert to just using the z distribution again, and we just change up our formula because we're changing up our parameter. Our parameter in that case is p, and our statistic is p hat.